So just to give you a glance, so we have one slide. Where are you? 1, 2, 3, 4, and we are done. And we are ice curves. But I'm not going to bother you with all this Greeks stuff. We're going to focus on the picture, on the schematics on the right bottom part, because you are going to see whenever you try to work with this, you are going to see a lot of those kind of schematics. So I would like to explain them to you, what they mean, so that when you are, if you decide to use the tools and when you read textbooks about it, you are going to see a lot of plots like this. So just to discuss what is what, you don't have to look, you don't have to, okay. Last day, and it's striking a little. So you don't have to look at the equations at all at the moment. We are going to focus on this part here, just to explain what is what. So these kind of schematics is called Gaussian network models, and they are used to describe equations like this. And this is quite easy to draw, and based on that, you can actually realize what kind of models you're describing. When you draw diagrams like this, there are nodes that are gray or filled and nodes that are white. The gray nodes means those points are our data points, and the white nodes are the ones that are parameters that we would like to fit. And the arrows shows dependency. So this means that this value of this theta should influence how these data points are generated. So let's go backwards. Let's say that we don't have data, but we have everything known up front. We know all the probabilities, everything, and we would like to generate this data. So what we are doing, we are taking the true value of theta and plug this value theta to the known probability distribution, and then start sampling it. And these axes start to pop up. What we actually have is, we have these measurements, and we would like to somehow find out what is this parameter theta. And this is the simplest form. For example, let us assume that we have y equals theta x, and we would like to find this parameter theta, and this equation is practically described by this plot. We can have more complicated stuff. For example, this theta influence some latent variables called z, and each of these z influences its own x. And we can start piling up these scenarios. And now what we have is something that is called, I think that we can use it like this, it's called Gaussian mixture model. Why is this important, and why I'm focusing on this? Because here is the point where Occam's razor pops up. This is the point where we are going to see that Bayes' rule actually inherently encodes the fact that Mother Nature favors simple models. From all the possible models, the simplest one should be the most probable one. And let's discuss how this works. So Gaussian mixture model, if you don't know what it is, it's assume that we have data that can be generated from multiple Gaussian distributions, each of them with a simple weight. So let's assume that we have like this. We have Gaussian distribution 1, so I'm going to call it P1, then a little different P2, maybe like this P3, and so on and so on. And then we say each of these has certain weight, and we start selecting, some time we select from this distribution, some time from this, some time from this, and we are getting data x1, x2, x3, and so on and so on. So we mix all these distributions in order to generate our data. And the question that we would like to answer, how many mixtures are there? That is our main goal. So in essence, if we have infinitely many of them, then everything collapses to a single Gaussian because of the central limit theorem. But let's say that we have a small number of them, and the question is how many. So let's describe this model. So what we have is, we have to somehow select these weights. This is our value P. So this value P is the probability which of these functions are activated. Then we have global covariance matrices, global mean values. We select one of those, and all these parameters now, this, and this, influence what are we measuring. And we measure n of this. So what does this mean? This square around means that everything in this square is repeated n times. And every repetition is so-called conditionally independent. So we can say that based on these values, x values are independent among each other. That's why we can use this multiplication. And the question is, what is the distribution of this? How many components should we take into consideration? And for Gaussian mixture models, we can start to derive this. I'm not going into any details. The derivations are here, and they will become quite complicated quite fast. You can go through it. Everything is derived in this Murphy book. What I would like to show is goes on and on and on. And what I would like to show is this result. When you come to this equation here, this is the final green distribution that we have. And if you solve this, you will see that this distribution is Dirichlet distribution, which is, if you don't know what Dirichlet distribution is, it is a distribution that somehow is capable of sampling from multiple dimensions variables that are from 0 to 1. So this Dirichlet distribution sets which is the probability of activating a certain Gaussian component in our model. And we would like to find out what is the dimension of this distribution. And when all of this is calculated, there is this bizarre function pops up. It's called this d gamma function. And if we draw it, it's this one. So why is this important? All this mathematics for something that's called d gamma function. What's the purpose of it? Well, it says the following. It says that under this scenario, when a certain component becomes, its probability of occurring becomes quite low, this model will immediately put it to 0, which means all this machinery tries by itself to remove as much components as possible until it cannot longer perceive that by removing an additional component, it will compromise the accuracy of the model. So it's like an aggressive cutter. It starts to cut as many components as possible while in the same time checks the accuracy of the model. And when it comes to a sweet spot, it stops by itself. So you don't have to take care of anything. This is built in all of this machinery. And if we go back to, let me see if I have a white slide here somewhere. No, let's go back. I have one slide. Yes. And also we can see this in the Gaussian, in the Bayes rules by itself. So this is our posterior. It is proportional to the likelihood times the prior. So imagine the following thing. So we say this prior is our belief about the model parameters. Let's say we have a model that is a simple linear equation. Theta is x plus b. No, that's right. Write it differently. X is ax plus b. So parameters theta are all the parameters of a plus b. So all of these are our parameters. And the question is, what is the dimension of these matrices? And now I'm going to show you how this is built in this old Bayes rule. I told you previously that we have to assume some kind of prior function. And if we have multiple dimensions, let's say that we have one dimension and we do it like this. So we say all theta parameters are equally distributed. And the height of this will be some value x. But then if I have two parameters, then I have to draw it like a 3D. So this is parameter A1, A2, and they can become here and here, and there is like a rectangular piece. But the height here is x2. Why? Because the probability, let me show it better. It is bizarrely strange. So that you can see it. You can do it like this, and then it's like this. So I have to draw like this. And the integral here must be 1. But also now the volume inside here must be 1. This means that the width of this cake, the height of this cake will be thinner. And if I go in multiple dimensions, the height of this now higher dimensional cake will be thinner and thinner and thinner. And this would mean that I will need to have more data, because my prior says that the model is really, really low. My prior knowledge is low almost everywhere. And I will need a lot of data to push this up sufficiently high in order to get some proper results. So what is the best case scenario for me is to take really simple model, because my prior information will be sufficiently above 0, and I will need just a little information to get the proper output. If I have multiple starting points, I will have to put a lot of effort just to jump out of these thin layers of cakes and to have something logical. This is actually built in the Bayes rule, but it's hidden from the side. When I explain it like this, you are nodding, saying, "Oh, right, Occam's razor is built in here." So Bayes rule by itself favors simpler models. Simpler models will result into better fits, which is logical. But there is a sweet spot. If I cut my model extremely, it won't be capable of doing fits anymore. We can see it if, for example, if we have like points like this, noisy points, one can say, okay, I can fit a linear model like this. Then we can say we can fit maybe a parabola like this. And if we allow, I don't know, 20 or two polynomial of order 20, it can do like this. It can fit all over the place. It can catch each and every point. But all of us are going to say, look, the grid one is the best. Why? Because Bayes rule is built in our behavior. We always want to find the simplest model. So this is where all of this comes out. And if we go through a lot of mathematics, through the methodology that I was explaining today, this thing pops up on this slide as this d gamma function. So now the question is, we have a methodology that is capable of finding the simplest model based on our data, whilst in the same time it fits the model parameters. Can we use it for our ice curves? Finally, let's see how all of this has any implication to electrochemistry. Okay, maybe I should click here. Okay, this is what we have at the moment. So this is an experiment, I think, from the same experiment actually that I'm dragging around all this week, these 600 ice curves. You can see the gap in the middle. So these are 600 or I don't know how many on this field consecutive ice measurements. And one can say, okay, no, they're not 600 consecutive because otherwise they would have been all over the place. Let's say, it's written 10 consecutive ice measurements. And we can see that they wiggle around. And the question is, how much of this wiggling around is noise? And how much of the wiggling around is the actual change of the ice curves? So I'm going to use all this machinery that might be at first glance seem completely overkill to try to answer this question. So I'm going to fit first equivalent circuit models, and then I'm going to try to find which model is the most accurate. Okay. As I've already said, first let's do simulations. So we have a model with 3 RQ elements. They are clearly visible as 3 arcs here. And when we're doing simulations, we inherently impose quite a lot of noise in the data. And our calculated ice curves are the black dots that you see behind. And because of the noise, the ice looks as it here on the plot. On the right hand side in the table, you can see the parameters that we used. And the second column here, okay, well, this is becoming a nuisance. The second column here are the initial values that we used. And now to answer your questions, how did we come up with this? Okay, so let's go one step at a time. When you look at the ice curve like this, you can immediately say that just by eyeballing it, you can say, look, the serial resistance is around 3. I don't care, is it 3.1, 3? It's around 3, okay? This is the easiest part what we can do. And then we have to say, okay, what is the green candidate PDF that we would like to fit? We have to decide that, 2 things. So we say, okay, this is a resistance. We can say that the resistance can be 3 plus minus whatever we think of. And then this would mean that the resistance is a normal distribution. But in order to be picky, let's draw a normal distribution, let's say like this, and we said it's 3, and we draw like this, and we say this is our serial resistance. The problem with this, at the first glance, there is not a problem. But a normal distribution is defined from plus to minus infinity. Yes, it drops rather sharply, but there is a probability, extremely, extremely low one, but still there exists, that I can draw a negative resistance, which is physically impossible. So this means that I should not choose for my green distribution to be a normal one. So I should choose a distribution that has only positive values. one of the simplest way to do it is to use so-called log normal distribution. I'm going to show it to you how it looks. If you cannot visualize it, it's rather simple. Come on, cooperate. So log normal distribution. I have it here. Jesus, forgot about it. I didn't have to jump. So a log normal distribution is the one that we have it here. And as we move the mean value towards higher values, just by eyeballing it, you will say that it is similar like a normal distribution. Yes, and that is what we like. But mathematically speaking, it is defined only on positive values from 0 onwards. So there is no way to sample negative values. That is why for all these parameters that are strictly positive, we use log normal distribution. However, mean value and the variance are rather convoluted. So we usually think like, oh, I would like to have a value of 3 plus minus something. These equations on the right-hand side, convert Gaussian style parameters to a log normal style parameters. And that is how we came up with these parameters in our tables. All of them for log normal. Regarding these intervals for Q, those intervals for Q are also rather simple. You know the frequency range of your measurements. You've already decided that you will have 3 components. I'm going to come to the point how we decided it. So just by a rule of thumb, you can more or less say that, okay, I need 3 points. I can put them equidistantly or logarithmically spaced within the frequency interval where I look, plus some confidence interval. And then you get all the combinations RQ, RQ, RQ as starting points. And from here you can fit it. The final thing what we have to decide are the alpha parameters in our equivalent circuit model. So alpha parameters are usually in the interval from 0 to 1. We can always say that it is a uniform distribution, but we can complicate it a little bit, because uniform distribution is just a special case of something that is called a beta distribution. And this is how beta distribution looks like. Why is it better? Because we have 2 parameters, alpha and beta. And by doing so, we can skew it. So for example, instead of making it uniform, we can make it like this. It is defined always on the interval to 0 to 1. And we can say that we believe that our alpha parameters are from 0.6 to 1. And I can choose this value here. And by doing so, I can somehow push my optimizer like, look, this is my prior belief. Please look for values above 0.6. And in such a way, just by choosing these distributions, you can help the optimizer to push the optimizer where to look. You are not saying to the optimization procedure in any way, don't look outside. There is a small probability for the optimizer to try to see these values, but majority of the time it will concentrate here. And that is the way how we are actually imposing this stuff. And this is where we entered with the distributions, and at the same time with the initial values. So if we start all of this, this is how the optimization process goes. As you can see, for example, for the Q parameters, the pink haze is confidence interval. So at the moment, at the very start, the distribution of these parameters is rather wide. The process is not certain about their values, but as the optimization progresses, the uncertainty falls, and then everything becomes quite consistent and quite constant. And at the end, what we are getting at are the following values. So the blue dots, the blue lines, are the final distributions of our equivalent circuit model parameters. And these are their final distributions, and we can draw them. One might argue that all of them are Gaussian, right? They look like, but formally they are log normal. Their values cannot be negative. So mathematically speaking, the results are completely in line with the reality that we're expecting. The last row, where is it? No, the second row here are the alpha parameters. Again, one might argue that they look like Gaussians, but in essence, they are beta distributions, and the values of alpha cannot go below 0 or above 1. So everything is physically sound, and these are the values that we got. So because we used all of this machinery, we said, okay, if we have a lot of time on our hands, let's do Markov chain Monte Carlo sampling, because Markov chain Monte Carlo is going to give us the actual true distributions that are in the model. And we run it for a couple of hours, which is practically useless, but we just wanted to confirm our results. And the pink PDFs that you're looking at here is the true posterior. And you can see in some cases we made wrong assumptions. Maybe the distributions were not log normal. Maybe in some cases beta parameters are not properly enough or whatever. But compared to a couple of hours of sampling, the blue lines were evaluated in less than 20 seconds. We can say, yes, we know that we have bias. We know that it is not completely accurate, but it's quite okay because all of the distributions overlap. So for the speed up that we made, for the numerical efficiency that we made, this is the price that we are paying. So let's go now to more bizarre scenarios. What can we do if we test how the noise affects our measurements? So if we have noiseless simulation, then this is the top row. Then we see on the right-hand side, our fit also says that all the parameters are spot on, as it should be done. As we start increasing the noise, this haze, the pink haze, starts to increase. So this means that we are less and less certain about our results. If we put a bizarre amount of noise, then we have the third row here, and the eyes, if you can say it, its eyes are this blue Picasso line. Oh no, sorry, the black Picasso line on the last graph. And from the black Picasso line, we can estimate the blue one, and everything is covered in noise. So we can immediately say that the results that we got, we are really not confident in them. And this is an extra feedback that we can get from our models. We can immediately say that maybe the fit looks fine, but the noise in the estimates is so big that someone should double check what the hell is happening. If we go even one step further, let's take real case scenarios. So these are the parameters of the ECM from the previous ice curves. So yes. So let's go into a real case scenario where we try to fit impedance data. So we take 10 consecutive impedance measurements and try to estimate where is the true value of the impedance and how much of these values, how much of these changes are noise and how much is the actual change in the system. In particularly, we should be interested in this spread here, and also this noisy part in this case. Is it noise, or is it something strange happening in the system? These are final results, and I'm going to show how we came up to this. So the final results are saying that this is the true curve, what we are getting, the estimated mean, the red one, which is behind, and our confidence that this is the true line is this pink haze around it. So we can safely say to some extent that this here is not an effect of the ice curves, but maybe effect of noise, effect of our imprecise analysis. And also this is true for the low frequency part where noise is mostly is affecting our ice curves in the most severe manner. So if we fit now the same parameters, we can see that unlike the simulations, the width of this uncertainty region is quite big for quite longer time, but it eventually settles down. And the final fits look like this. Again, we took a couple of hours of Monte Carlo versus around 30 seconds of variational Bayes. We can see that on some cases, like here, we do make some mistakes, and particularly here. But for the speed up that we get, these mistakes are only a couple of %. And we think that the speed up that you are getting justifies not to use Monte Carlo, but to use this variational Bayes approach. And now we have the issue of can we use this approach to make fuel fall detection? In this case, we have 3 sets of ice curves. They're real experimental data where we have different type of fuel utilization and 1 leakage fault. And each of these ice curves separately was used to fit such an equivalent circuit model. Some data have greater noise uncertainty around it, some others don't. And on the right-hand side, you can see the differences in the model parameters. And because we have here probability distribution functions, we can use any form of comparison among PDF to see statistically significant changes. Some of them are extreme, but some of them are rather close, and you can quantify them. Are they sufficiently different or not? And in such a way, you can do an automatic fault detection in the process. Finally, what I'm going to show you in this next maybe 5 slides, and that is where I'm going to end, is how all this machinery can be used to find the most probable order of the model that we are using. So, as I was saying during my first days of presentation, because we have fractional order systems, currently we do not have any methodology that can reliably tell us how many time constants, how many peaks in the DRT curve are we going to use. So in this case, I'm going to use this trick of variational Bayes approach that has built in Occam's razor that tries to pile out the simplest model that is in the same time accurate enough. So what I have here is, as previously, we have a serial resistance, and we say that this is a log normal with these parameters, so strictly positive. Then we have n poles, and I don't know which is the true n. And for each n, I have value of the resistance, time constant, and fractional order parameter. And all of these are entering into my ice curve with some noise level, and these are my measured data. And based on this, I would like to find which model is the most probable one. So I'm not going into the equation, anything. No, this is actually quite important. And this one. We have to, because we have a summation in our equivalent circuit model. So our equivalent circuit model is this Z omega sum I from 1 to maximum number of poles R Y 1 plus S alpha Y tau Y. When we say give me the first 3 poles, it doesn't mean that I ask the model to give me poles number 1, 2, and 3, but I'm asking the model, give me the 3 most dominant poles. And which poles are most important, or actually which time constants are most important, is done by something that is called pole importance. It is something that was developed for batteries first. Here is the reference if you would like to check, and it is a solution of this integral. And it gives us which time constants are the most important for the behavior of our system. In general, what does it mean? It means, let me see if I can find, no, I don't have a plot like this. I'm going to draw it out. Imagine that we have assumed 6 poles in our system, and we draw a DRT curve of it, and it will have, for example, 2 really small peaks, 3 really big ones, like this, and here. So I have peak number 1, peak number 2, 3, 4, 5, and 6. And when I say give me the 3 most dominant poles, this equation actually will pick up not the 3 highest one, but the 3 poles that have maximal area under them. That is the idea of this pole dominance. And it will say this time constant, for example, this and this are important for a model with 3 time constants. If I say I want 4, I guess that it will add, for example, one of these. This will be the 4th, and so on and so on. So this is the part that was developed for batteries that turns out to be quite useful. So let's see how this works actually in a real world system. So what we have here is we assume that our observed data can have maximum of 5 time constants. How can we come up with this number? Well, we know the chemistry that happens in our system, and we have some pretty good background knowledge how many diffusion processes occur inside or whatever. And we can easily, around a rule of thumb, say that it is highly unlikely to get a model above, I don't know, 6 time constants. So this can be quite easily extracted based on our prior knowledge. And then our goal is, based on these models, to try to find the proper one. And in this case, what we have here, I'm going to simulate our true system will be the one with 3 time constants, and I'm going to have 5 candidates and try to find the proper one. And this is where I calculate the elbow loss for each model separately. So I fit the first model, the blue one, the second, the orange, the green, and the red. And I can see that the best models, the ones that achieve minimum loss, are models with poles 2 and 3. And I know the true model is model 3. So I can safely say that all this machinery that I was talking about, that elbow loss includes this Occam's razor itself, is actually working. So let's try it in a proper Bayes scenario. So we say, fine, give me all models and simulate them together, and take out which model is the best one. And I say at the beginning, all models have equal probability. and just start it. And the process goes on, and at some point it decides that model with 4 parameters is better, and at the end it decides that that one is the best one with 80% probability. So after the optimization, this algorithm will told me that a model with 4 time constant is 80% probable in this scenario, although I know that the true model has 3 parameters. This was partially, there are 2 effects coming into effect here, partially due to entered noise, and partially due to improper implementation of this categorical distribution. So I will come back to that. If I now try the same approach on real world parameters and try to fit this curve here, try to fit the ice curve with that is with blue dots, this one here, and I have model options with 7 poles. At the end, it says that the true value is will have 5 poles. These are experimental data. And if I draw the DRT based on this analysis, what I can see is the model actually made a mistake. What I got is 1 time constant, 2nd time constant, and it put 2 time constants at the same spot, which means that these 2 are actually 1, and another one here where I have a lot of noise in my measurements. So it was to some effect an overconfident and provided a little a more complex model than the actual value. Finally, what we did is we took these 600 ice curves that we have, and we tried to estimate the model order of each and every one of them. And we can see that the majority of them turns out to have 6 poles. Some of them are jumping between 6 and 7. And the points where we have fuel utilization or some major fault, it required less complicated models. But still, we would have liked if the values here were fixed, not so noisy. And in our experience, 6 number of poles, 6 turns out, it seems a little bit overcomplicated. So we realized that there is a numerical issue, how this was implemented in the process behind. I'm not going into any details. There was a trick that instead of using Dirichlet distribution, which is really, really complicated, you can use something that is called logistic normal approximation. Why is this important? This is important because the Dirichlet distribution doesn't have nice gradients, and the optimization with gradient descent has a lot of trouble. This form of equation can be differentiated quite easily. It has exponents, logarithms, and products, and this is really, really easy to do. And if we just change this into results above, this is what we get. The same amount of data, everything the same. So at the beginning, the algorithm doesn't know which models to choose, but when it converges down to a proper value of 4 poles. The right-hand side is the true pole, and just behind it is the fitted value. So just by doing this change, we are now quite capable of taking an ice curve, and based on the ice curve, capable of providing a value how many DRT peaks you are able to see in the ice curve, and by doing so telling you how many, what kind of equivalent circuit model is the most probable one. This doesn't mean, but take care, this doesn't mean that what we are proposing is the actual truth. We are saying that based on the data that you have collected, which means based on the noise levels in your data, based on the frequency bands on your data, this is the best thing what we can take out. This doesn't mean that it is the truth, it is the truth, it is the best thing that we can extract from the data. So going back to my slide of the Bayes rule, when we are throwing this ball back on the table, but we have imprecise measurements how far we are from the true ball. And based on these imprecision measurements, we are saying that regardless where the actual ball is, this is the best what you can expect from your data. Usually, the problems that we run into are the following, especially in the SOFC community. There are cases where there are certain mixtures of gases coming into in the solid oxide cell or stack, and one would expect to see at least 6 diffusion processes. And we are saying, no, you can see here only 4. And the answer would be no, you're doing something wrong. There are 6 diffusion processes. What is happening? There must be 6 DRT peaks. We're not saying that the model is wrong. We are just saying that there are several options, actually. We are saying the following. Either some of the time constants are not excited properly and they're buried in noise. They're present in the signal, but we are unable to see it because they are buried in noise. Second option is that 2 time constants are so close to each other that we cannot distinguish them. And the third option is maybe some of the time constants are outside of the frequency range that we measured. This doesn't mean that those time constants are not present. The only thing what does this tell us is that we are unable to distinguish more than 4 poles in the current settings of your signal. Either you improve the signal to noise ratio, change the frequency range, or I don't know what. Currently, the evidence in the signals provide only 4 poles. And this is not a rule of thumb. This is based on all of this machinery, and this is the number where Occam's razor comes in. So what we are saying is, based on the observed signals, on the observed evidence, the simplest possible model that provides sufficiently accurate results is the model with 4 time constants. And this procedure can be applied for any additional measurements, and it can be used as an efficient estimator of model complexity. So this is the point where we are currently. This is the final result that I wanted to show you. It is not a formal method that solves the issue how to identify these models, but at least we are not in the dark. We now have at least a formalized way to get some reasonable assumption about the complexity, and we can use it as a starting point.